Hey everyone, this is Trayman again from Team 16, Block Portability. In this video, we are excited to give you a more in-depth look at what our sponsor, Michigan Foam Products, has had us working on for our senior design project. MFP proposed that our team develop a better system for loading, transporting, and placing their large foam blocks into and out of storage. Along with maintaining a safe way to transport them, MFP wants to enable first-in, first-out practices. In addition, they requested the development of an inventory system to track block locations and store each respective block's specification data. These foam blocks measure at 3 feet by 4 feet by 16 feet and can weigh up to 650 pounds. As you can see, the current process involves frequent manual manipulation of product and does not satisfy the company's goals for safe, ergonomic practices. At the moment, only a fraction of existing operators are able to perform the loading and unloading operations due to the physically demanding process. To further understand the task laid out in front of us, a number of specifications were developed in partnership with MFP, which gave specific deliverables for any working prototypes. These specifications were broken down into separate categories, one being those related to the transportation of foam blocks, one for the storage of foam blocks, and the last for the inventory management system. For the transportation device, the key specifications we came up with are highlighted as follows. First, the dimensions of the transport device should not exceed 48 inches in length by 24 inches in width by 3 inches in height. These dimensions mimic the dimensions of the cart currently in use at MFP so that the prototype can continue to interface with the block tippers already in place, avoiding the need to modify or replace existing equipment. Second, the load capacity of the transport device was set at a minimum value of 813 pounds. This value applies a factor of safety of 1.5 to the heaviest foam block that MFP is capable of producing. Third, the maximum pushing force required to move the loaded transport device should not exceed 25 pounds when moving a distance further than 10 feet. This specification addresses ergonomic concerns raised when transporting blocks and adheres to OSHA safety standards. Finally, as with the previous specification, the maximum pushing force required to move the loaded transport device should not exceed 50 pounds when moving a distance less than 10 feet. This specification also comes from OSHA safety standards and regulations. For the storage system, the key specifications we came up with are highlighted as follows. First, the load capacity of the storage device was established as a minimum requirement of 11,700 pounds. This applies a factor of safety of 1.5 and accounts for a fully loaded row of storage equating to 11 blocks weighing 650 pounds each. Second, the maximum storage dimensions for a row of foam blocks was set as 450 inches in length by 50 inches in width by 198 inches in height. These dimensions were based on desired values provided by MFP using floor design plans for future buildings and serve to enable MFP to fully utilize the floor space throughout their buildings. The third and fourth specifications are identical to those found for the transportation device, as the same OSHA safety standards applied to the manual pushing of foam blocks whilst they are in storage. Lastly, for the inventory management system, the key specifications we came up with are highlighted as follows. First, the system must accept and store block information as inputs to the system. This includes all relevant information desired by MFP, mainly customer codes and block density. Second, the system must give recommendations for block locations when being added into storage. This specification was created based on the desires of MFP to organize their inventory in a more efficient manner, leaving less room for error. Third, the system must allow an operator to search the database for a block based on the inputs mentioned in the first specification. Lastly, the system must provide a visual representation of the data being collected so that it is easily accessible on the shop floor for both operators and management. This last specification targets the desire of MFP to improve communication between operators and managerial staff so that everyone can know what's going on at any given time. With a list of specifications established and agreed upon by all parties, our team set out to deliver on these objectives and devised a working prototype which has done just that. For block transportation and storage, our prototype utilized a modified version of the existing transportation devices at MFP with the addition of a hydraulic lift to raise and lower blocks in storage. This design choice allowed us to easily meet the first key specification, as the outer frame of the prototype can be seen pictured with dimensions that match those of its predecessor. Further, the prototype can be seen successfully interfacing with the block tippers found in molding and production. Testing was conducted using a measuring tape to confirm the dimensions of the prototype, which was found to be 48.5 inches in length by 24.4 inches in width by 3 inches in height. To ensure that the transport device exceeded the minimum load capacity required, calculations were performed prior to any machining. These calculations can be seen here. Upon machining and assembling the prototype, physical testing was performed on the device using an admittedly makeshift setup where multiple team members piled onto the device alongside a foam block of a known weight. The results of this test were successful. For pushing force specifications on the transport device, calculations were performed prior to assembly. To do so, the friction coefficient of the caster wheels on the device was received through the manufacturer. These calculations used a weight higher than the actual weight of the transport device, though further physical testing was performed using a force gauge to ensure that the calculations were accurate. The results of these tests are depicted in the table, which showcases different block densities and the pushing force required to move them. Moving on to the storage system, blocks that have been recently molded are loaded onto pairs of rollers in the back via our transport device, where they can either be manually pushed toward the front of the row or driven to the front with minimal resistance. The rollers keep the blocks from being stored on the floor and serve to mobilize the products so that the transport device can be used to easily retrieve a desired block. To meet this first specification, data provided by the manufacturer was used in calculations to show that the rollers could support the required load capacity with plenty of room for error. Physical testing of this specification was not performed due to a lack of resources and was acknowledged by MFP. The selected rollers also meet the second application mentioned earlier, as the outer dimensions for each row were measured and are depicted here. The final specification for the storage system, the pushing force, was met through a process of careful selection of materials. By using the calculations seen here, a theoretical pushing force was determined prior to purchase that was well below the designated limits. Though the actual data did not match the theoretical calculations, physical testing proved that the pushing force was still within the designated limit even for a full row. The graphic seen on the right showcases the different densities used at MFP versus the pushing force required for a full row of 11 foam blocks of that density. Before moving on to the inventory management system, one final specification that was not mentioned for both the transportation and storage devices was the desire of MFP to enable FIFO practices. For the unaware, FIFO, or first in, first out, is a common manufacturing practice that emphasizes sending products out in the order they were produced. At MFP, this meant that the new system should enable operators to pull foam blocks from inventory in the order they were molded in. As has been hopefully seen, the combination of the transport device and the storage system was carefully developed with this practice in mind, since blocks ready for production will gradually flow to the front of the aisle to be transported to production via the transport device. Finally, for the inventory management system, an application was developed to be compatible with handheld scanner devices used on the shop floor. Rather than manually inputting data, operators can now scan QR codes that are automatically generated with each new order and printed onto existing labels seen here. The application allows operators to add, remove, and search for blocks while also allowing management to import and export inventory data for their own viewing and analysis. In addition, the application automatically updates a visual display monitor, which has been purchased and will be set up on the shop floor. This visual display provides a simplified view of all inventory currently in the database, including important information about the block. As the specifications for this portion of our project were not measurable, the approval of these specifications was done in conjunction with MFP through several rounds of hands-on testing. Here is a video demonstration of the key specifications listed for the inventory management system. As you can see, the application successfully allows the user to scan, add, remove, and search for a block in inventory. A more detailed functionality presentation and user guide was made and provided to MFP for future use. I'll let this video play out to showcase the full functionality of the app. With that, I'd like to conclude this longer video presentation by saying thank you for listening. We'd again like to thank Michigan Foam Products for sponsoring this project, Dr. John Ferris and Dr. Chris Pung for their work as mentors, and the GVSU Machine Shop team for their assistance. Go Lakers!